Hello and welcome to QED Lecture 5 Part 8, the t-test of correlation. Looking to test a correlation between two variables, and what you need is a random sample from the population, and you need to have scale variables x and y. You can use it with ordinal variables in some situations, but often you might be better off using a different form of correlation coefficient, such as the Spearman's correlation coefficient, or possibly transforming the variables. So for now, I'll assume they're scale variables. So the null hypothesis is that in the whole population, those variables x and y are not correlated. The alternative is that in the population they are correlated, and that's a two-sided one. You can also have one-sided hypotheses. They're positively or negatively correlated. I didn't write those out. Base of the calculations, again, in purple, so we wouldn't expect you to know that in QED, but you can show that if that null hypothesis is true, and also there's some further assumptions that x and y are both normally distributed. In that case, that if you calculate this, where r is your Pearson's, the standard correlation coefficient, and n is how many you have in your sample, so if you work that out, which looks a bit horrible, that then would follow a t-distribution with n minus 2 degrees of freedom, and you look up probabilities in Excel as usual. So let's go straight to an example. Looking at connection between putting fertiliser on and getting maize out. So does increased fertiliser use on small farms raise yields? Well, you'd hope it would, so you'd hope for a positive correlation. So the null would be, in the whole population, fertiliser application rates and maize yields are not correlated. So that's the whole population, and we just got a sample from that population. The alternative would be that in the whole population, they're positively correlated. So you'd hope that more fertiliser gives you more maize. Before you do a test, it's a good idea to just have a sense check by doing a scatter graph, looking at correlation coefficient, saying, does that make sense? And indeed, it kind of looks sort of like, maybe not a bit non-linear, but it looks like kind of positive correlation then, and certainly that's quite a high coefficient. However, there's always a chance that it's just random. So it could be that if you imagine these were just stones or peas and you threw them onto here randomly, what's the chance that just randomly you could get something that looks just a strong correlation as that? Is that possible? Well, it is definitely possible. How likely is it? And that's what you can test by either using the formula, using Excel, or what you can just do is just do it in Stata. That's fine for QED. So put the data into Stata. This is the command. So pairwise correlations, fertilizer maize. So you've seen this part before. This just gives you this correlation coefficient. And sig just makes sure that it gives you the two-tailed significance. So you should know why these are ones, because that's the fertilizer and maize correlated with themselves. Not very interesting, perfect correlation. But here's the correlation between fertilizer and maize. That's the value you had before, 0.6. This is the sig value. We're going to divide this by 2. So can you think, why am I going to divide that by 2? Pause and think about that. Okay, the reason we're going to divide it by 2 is that if in the whole population there's no correlation between fertiliser and maize, then if you pick many, many samples, the expected value, what you should get here is 0. Sometimes you get negative, sometimes you get positive. So in the whole population it would be 0, but when we pick our sample, we know we won't get exactly 0, but we want to know what's the chance of getting something as big as this, but positive only. If we got negative 0.06, but then we would not reject the idea that in the population there's no correlation. So we're only going to reject if we get positives. This probability is that's the probability of getting a number as big as this, either positive or negative. Because in this test we're only looking for positive, it's half that. So divide that by 2 to get this. So if you're doing a one-tailed test here, you've got to do that extra work yourself, divide by 2. Okay, so having done that, all the calculation completely different from the previous 2 tests, but this part is the same. Once you've got the p-value, what should you do with this in terms of this menu of options? So please pause the video, think of that. If that's your p-value, what's your selection going to be here? So pause and think about that. Okay. So because this p-value is less than 5%, less than 0.05, you can reject at 5%. It is not less than 0.01, so if this is not correct, you can't reject at 1%, but it is less than that, so you can reject at 5% because it's less than 0.05. So B is the correct answer here. So we found a p-value below 0.05. Reject H0 at the 5% significance level. Remember to put the conclusion in for the non-technical readers. That means the evidence provides fairly strong support for the view that farmers who apply more fertiliser do enjoy high maize yields in the population. So in the next section we'll go on to another kind of test for a different type of data called the chi-squared test, but for now, thank you for watching.